We will now conclude our study by looking at the operational properties of the Laplace transform. So the first one is known as the first translation theorem. And it says that if L of f of t is equal to big F of s, and a is any real number, then the Laplace transform of e to the at times f of t is equal to big F of s minus a. We're going to go ahead and use this to solve the initial value problem. Y double prime minus 6y prime plus 9y is equal to t squared e to the 3t. Y of 0 is equal to 2. Y prime of 0 is equal to 17. And again, you could solve this using the method of undetermined coefficients. However, we're going to use Laplace transforms, so if we take the Laplace transform on both sides, now here we should notice that f of t is t squared and a is equal to 3. We should also know that the Laplace transform of t squared is 2 over s cubed. So these are just side notes. So we go ahead and take this Laplace transform. We're going to wind up with s squared times y of s minus s times y of 0 minus y prime of 0 minus 6 times s y of s, I almost wrote x, minus y of 0 plus 9 y of s is equal to, now we're going to use the first translation theorem, so it's going to be 2 over s cubed evaluated at s minus 3. So it is 2 over s minus 3 cubed. Pull all of our y of s's together. S squared minus 6s plus 9 all times y of s. Now we get minus s times y of 0, and y of 0 was 2, so minus 2s plus minus y prime of 0. Y prime of 0 was 17. Plus 6 times 2, which is 12. Simplify this. And that whole thing is equal to 2 over s minus 3 cubed. Which means that s squared minus 6s plus 9 all times y of s is equal to 2s plus 5 plus 2 over s minus 3 cubed. And so y of s will be 2s plus 5 all over s squared minus 6s plus 9 plus 2 over s minus 3 cubed times s squared minus 6s plus 9. But s squared minus 6s plus 9 factors to s minus 3 squared. So we have 2s plus 5 over s minus 3 squared plus 2 over s minus 3 to the 5th power. We will want to write this first fraction in partial decomposition. We can leave this one alone. So we'll have 2s plus 5 is equal to a times s minus 3 plus b. Solving this yields b is equal to 11, and so a must be equal to 2. So we now have y of s is equal to 2 over s minus 3 plus 11 over s minus 3 squared plus 2 over s minus 3 to the 5th power. Which means that y of t will be the inverse transform of 2 over s minus 3 plus the inverse transform of 11 over s minus 3 squared plus the inverse transform of 2 over s minus 3 to the 5th power. The inverse transform of 1 over s minus 3 is e to the 3t, so we're going to have 2e to the 3t plus 11 over s minus 3 squared. Well, the inverse transform of 1 over s squared is t. So using the second translation theorem, this has to be t e to the 3t. Plus 2. Now this 1 over s to the 5th power, the inverse transform of that is 1 over 4 factorial t to the 4th. And then second translation theorem says this will be e to the 3t. So 4 factorial is 24. So as our final solution, e to the 3t all times 2 plus 11t plus a 12th t to the 4th. We will now look at the second translation theorem. However, before we do that, we need a definition. The unit step function u of t minus a is defined to be a piecewise function. 0, whenever 0 is less than or equal to t, less than or equal to a, just less than a, sorry, and 1 whenever t is greater than or equal to a. Now we can look at the second translation theorem, which states if big F of s is the Laplace transform of a function f of t, and a is greater than 0, then the Laplace transform of f of t minus a times u of t minus a is equal to e to the as times big F of s. An alternative form, Laplace transform of g of t times u of t minus a is equal to e to the negative as times the Laplace transform of g of t plus a. And of course this means that the inverse transform of e to the minus as times big F of s is f of t minus a times u of t minus a. My apologies, up here this should be the Laplace transform of f of t minus a times u of t minus a is e to the negative as times f of s. So we're going to use the second translation theorem to solve the initial value problem. Y prime plus y is equal to 0 whenever 0 is less than or equal to t less than pi, and it is 3 cosine of t whenever t is greater than or equal to pi. Now, what we note is that this function is 3 times cosine of t times the unit step function of t minus pi. So let's go ahead and take the Laplace transform. So we're going to have Laplace transform of y prime plus y is equal to the Laplace transform of 3 cosine of t times u of t minus pi. So we get s times y of s minus y of 0 plus y of s. I'm sorry, the initial condition was y of 0 is equal to 5. So this is equal to, you can factor out that 3. Now we have the Laplace transform of cosine of t times u of t minus pi. Using the second translation theorem, this becomes 3 e to the negative pi s times the Laplace transform of cosine of t plus pi. However, cosine of t plus pi is the same as negative cosine of t. So we now have negative 3e to the negative pi s times the Laplace transform cosine of t, and the Laplace transform cosine of t would be s over s squared plus 1. So we're going to have s plus 1 times y of s minus 5 is equal to negative 3 s e to the negative pi s all over s squared plus 1. Which means that y of s is equal to 5 over s plus 1 minus 3s e to the minus pi s all over s plus 1 times s squared plus 1. Let's take a look at 3s over s plus 1 times s squared plus 1. So we're going to have 3s is equal to a times s squared plus 1 plus b times s plus 1, which is equal, I'm sorry, bs plus c times s squared plus 1. So what are we going to have? We're going to have an a plus b. This should be s plus 1. A plus b times s squared plus b plus cs plus a plus c, and of course that all equals 3s, so we can use coefficient comparison to set up a system, and we'll get a is negative 3/2, b is positive 3/2, and c is positive 3/2. So y of s is equal to 5 over s plus 1 minus 3/2 times the quantity of negative e to the minus pi s all over s plus 1 plus s e to the minus pi s all over s squared plus 1 plus e to the minus pi s all over s squared plus 1. So y of t is the inverse transform of 5 over s plus 1 minus 3/2 times the inverse transform. I'm going to make this plus e to the minus pi over s plus 1 minus 3/2 inverse transform of s e to the minus pi s over s squared plus 1 minus 3/2 inverse transform e to the minus pi s all over s squared plus 1. So the first inverse transform is simply 5e to the minus t. The next three are all going to use the second translation theorem. So we'll have plus 3/2 e to the negative t minus pi times the unit step function of t minus pi minus 3/2 cosine of t minus pi times unit step function of t minus pi minus 3/2 sine t minus pi times unit step function of t minus pi. Simplify all this a little bit, so we have 5e to the negative t plus 3/2 e to the pi minus t, step function of t minus pi, plus 3/2 cosine of t, step function of t minus pi, plus 3/2 sine of t, step function of t minus pi. So that becomes 5e to the negative t plus 3/2 times the quantity of e to the pi minus t plus cosine t plus sine t, all times the unit step function of t minus pi. So therefore our general solution is a piecewise function. 5e to the negative t, the first piece of the step function is 0, so just plus 0. The second piece, 5e to the negative t, plus now this step function is 1, so it'll be 3/2 times e to the pi minus t plus cosine t plus sine t. Here t is greater than or equal to pi, and this one is 0 less than or equal to t less than pi. Now, assume f of s is the Laplace transform of f of t exists and it is possible to switch the order of differentiation and integration. Now if we look at dds of f of s, by definition this will be dds of the integral from 0 to infinity e to the negative st times f of t dt. And since we can switch the order of differentiation and integration, this is the integral from 0 to infinity of partial s of e to the negative st times f of t, now dt. So this is equal to negative integral from 0 to infinity of e to the negative s of t, f of t, dt, which is equal to the negative Laplace transform of t, f of t. Now, if we look at the Laplace transform of t squared, f of t, this is the Laplace transform of t times t, f of t, which is negative dds of the Laplace transform t, f of t, which is negative dds of negative dds of the Laplace transform of f of t, which winds up being d squared ds squared of the Laplace transform of f of t. If we continue in this manner, we get the following theorem. If f of s is the Laplace transform of f of t, and n is a positive integer, then the Laplace transform of t to the n, f of t, is equal to -1 to the n times the nth derivative with respect to s of big F of s. So let's use this theorem to solve the initial value problem x double prime plus 16x is equal to cosine of 4t under the conditions that x of 0 is 0 and x prime of 0 is 1. So we're going to have Laplace transform x double prime plus 16x is equal to the Laplace transform of cosine of 4t. So s squared times big x of s minus s times x of 0 minus x prime of 0 plus 16 big X of s will be equal to s over s squared plus 16. So s squared plus 16 times big X of s minus 1 is equal to s over s squared plus 16. So big X of s will be 1 over s squared plus 16 plus s over the quantity of s squared plus 16 squared. So x of t is the inverse transform of 1 over s squared plus 16 plus the inverse transform of s over s squared plus 16 quantity squared. Now take note that if we integrate s over s squared plus 16 quantity squared with respect to s, we wind up with negative a half s squared plus 16 to the minus 1. So we have the inverse transform of 1 over s squared plus 16 minus a half times the inverse transform of, keep this plus, -1 times the derivative with respect to s of 1 over s squared plus 16. This first one becomes a quarter inverse transform of 4 over s squared plus 16. Now the second one, we'll get an eighth times the inverse transform of -1 times the derivative of 4 over s squared plus 16. Therefore, our general solution is a quarter sine of 4t plus an eighth t sine of 4t. So now we're going to look at a new operation called the convolution. So we have two functions, f and g, that are piecewise continuous on the interval 0 to infinity. The convolution of f and g is denoted f star g, and it is simply the integral from 0 to t f of tau times g of t minus tau d tau. So we're going to evaluate the Laplace transform of e to the t star sine of t. So by definition of convolution, this is the Laplace transform of the integral from 0 to t of e to the tau times sine of t minus tau d tau. I leave it as an exercise to the viewer to show that that integral evaluates out to a half times the quantity e to the t minus sine of t minus cosine of t. So we can now use the linearity of the Laplace transform. We'll have a half times Laplace transform of e to the t minus a half times Laplace transform of sine of t minus a half Laplace transform of cosine of t. So we get a half times 1 over s minus 1 minus a half times 1 over s squared minus 1 minus a half times s over s squared minus 1. So it's a half times 1 over s minus 1 minus 1 over s squared minus 1 minus s over s squared minus 1. So we get a half times s plus 1 minus 1 minus s. I'm sorry, these all should have been pluses. So that's going to change this. S squared plus 1 minus the quantity of s minus 1 minus s times the quantity of s minus 1 all over s minus 1 times s squared plus 1. And simplifying that will yield 1/2 times s squared plus 1 minus s plus 1 minus s squared plus s all over s minus 1 times s squared plus 1. So in the numerator, the s squareds will drop out, S's will drop out. We're left with 2, and so we're left with 1 over s minus 1 times s squared plus 1. It is also left to the viewer to verify the following property, which is the convolution fg is equal to the convolution of gf. That is, the convolution is commutative. Remember, this means that the integral from 0 to t of f of tau times g of t minus tau d tau is equal to the integral from 0 to t f of t minus tau times g of tau d tau. We now look at the convolution theorem, which states if f and g are piecewise continuous on the interval 0 to infinity, and of exponential order, then the Laplace transform of f star g is equal to the Laplace transform of f of t times the Laplace transform of g of t. So we're going to use the convolution theorem to solve a special type of integral equation. So we're going to solve the equation f of t equals 3t squared minus e to the negative t minus the integral from 0 to t f of tau e to the t minus tau d tau. So take the Laplace transform of both sides. Now, using the linearity of Laplace transform and the definition of convolution, we can write big F of s is equal to 3 times the Laplace transform of t squared minus the Laplace transform of e to the minus t minus the Laplace transform of f star e of t. Let me actually write that as f of t star e to the t. So Laplace transform of t squared is 2 over s cubed, so we're going to get 6 over s cubed minus 1 over s plus 1 minus, now the convolution theorem says this will be the Laplace transform of f of t times Laplace transform of e to the t. So we're going to get minus big F of s times 1 over s minus 1. And remember, big F of s equals all of that. Moving this over to the other side, we're going to have f of s plus f of s over s minus 1 is equal to 6 over s cubed minus 1 over s plus 1. So f of s will be 6 over s cubed minus 1 over s plus 1 all over 1 plus 1 over s minus 1. Now we just have to simplify that fraction. We want to write it as a single fraction, not a nested fraction. So this equals 6 times s plus 1 minus s cubed over s cubed times s plus 1 all over s minus 1 plus 1 over s minus 1. So we get negative s cubed plus 6s plus 6 over s cubed times s plus 1 all over s minus 1. And so we get s minus 1 times negative s cubed plus 6s plus 6 all over s to the 4th times s plus 1. Expand that out. We'll have negative s to the 4th plus s cubed plus 6s squared minus 6 all over s to the 4th times s plus 1. So use partial fraction. I will not use capital D because that stands for derivative. We've done enough of these. I'm not going to go through all that work. I leave it to the viewer that this will give you A is equal to 1, B is equal to 0, C is equal to 6, E is equal to negative 6, and F is equal to negative 2. And so big F of S will wind up being 1 over S plus 6 over S cubed minus 6 over S to the 4th minus 2 over S plus 1. So f of t is the inverse transform of 1 over s plus 6 times the inverse transform of 1 over s cubed minus 6 times the inverse transform 1 over s to the 4th minus 2 times the inverse transform of 1 over s plus 1. So f of t, 1 plus 3t squared minus t cubed minus 2e to the minus t. One final property to look at, transform of a periodic function. If f of t is piecewise continuous on 0 to infinity, of exponential order, and periodic with period capital T, then the Laplace transform of f of t is 1 over 1 minus e to the negative s big T times the integral from 0 to big T e to the negative st f of t dt. And we're not going to look at any examples for this one. I feel this is pretty self-explanatory. So that not only concludes this lesson, but that concludes our discussion on ordinary differential equations. I hope you've learned something throughout this course. I hope you've enjoyed it. And we will see you in the next one.